Good morning, my YouTube viewers. It is Crystal here, and in this particular video, what we're going to do is we're going to talk about logistic regression. Okay, so basically, when you are in machine learning, you basically have two types of machine learning models. One being a regressive model, which is what we covered in the previous videos of linear regression and multiple linear regression. And then you also have a classification model. And then so logistic regression is a type of classification model. And so although it says logistic regression on the title, it's actually a classification model. And so basically, when you have regression, like a linear regression, then what you have is you have like a flow. So the answer is going to be a flow. It's going to be several discrete values, and it can be a series of values, and it can be like whole numbers. But when you have classification problems, and logistic regression is a classification problem, then you're going to have like one of two values. And you also have something called multiple logistic regression, which is more than two values. So we're going to cover both of those types of logistic regression in this video. So logistic regression is used for classification problems where the dependent variable is binary, being success or failure. But there's also a way that you can do it for like more than two outcomes, and we will cover that in this video. So we're going to give you a demonstration of logistic regression. So the first thing that we want to do is we want to simulate our logistic data, and then we're going to do that by the first thing initially setting our seed. And when you set your seed, every time you run the program, the variables are going to initialize to the same value. So you do that by typing set.seed brackets 1, 2, 3, and you can put any number that you want in the brackets. And now we're going to define our predictor, which is our x variable. So x becomes seq, so you're making a vector, brackets neg4, 4, length dot out equals 200. So what you're going to have is you're going to have neg 4 and plus 4, and length dot out is 200. And then we're going to calculate the true probability using the logistic function. So P becomes 1 divided by brackets 1 plus exp brackets negative brackets negative 1 plus 1.5 times x brackets. Now we're going to define the binary outcome, which is your dependent variable. So y becomes r binom. So that's a randomly sampled binomial distribution of 200 samples with a size equals 1 and prob equals p. So prob is your probability. And then we're going to take our x and our y variable, and what we're going to do is we're going to convert it into a data frame. So my data becomes data.frame brackets x comma y, with x being your independent variable and y being your dependent variable. So we're going to define our model, and then we're going to fit it. So model equals, becomes GLM, and GLM stands for generalized linear model. Brackets y which is your dependent variable, tilde x, which is your independent variable. Data equals my data, family equals binomial. So that's letting you know that what type of distribution is going to be created. And then we're going to summarize the model. So you have summary model. So when you summarize the model, your formula is GLM brackets, formula equals y tilde x, family equals binomial, meaning it's going to be a binomial distribution, and data equals my data. Then you have your coefficients. So you've got the intercept, and then you've got your x variable. So you've got your estimate, your standard error, your z value. That means it's going to be based upon a z distribution, which is also a normal distribution, and your p-value. So your p-value in the intercept and the x is really low. So your significant codes, it gives you your significant codes, and it says dispersion parameter for binomial family taken to be 1. So you have null deviance is 272.117 on 199 degrees of freedoms, and you have residual deviance is 85.179 on 108 degrees of freedom. You have an AIC of 89.179, and your AIC is a goodness of fit test used in statistics and used in models, but I can't remember what it stands for right off the bat. And your number of Fisher scoring iterations is 7. So we're going to go back to the code. We're going to plot the raw binary data, jittered for visibility. So plot, brackets, my data, $x, comma, jitter, brackets, my data, $y, comma, amount equals 0.05, PCH is the size of the dot, is 19, color equals RGB, which is a vector to do with assigning colors, is 001, 0.4. Main is the title of the plot, is logistic regression R. XLab is your label on your x-axis, is X. YLab is your label on your y-axis, is probability of y equals 1. We're going to generate some smooth predictions. So X new becomes SEQ, which is a type of vector, brackets, min X, comma, max X, comma, length out equals 300. Predprob, that's a prediction of the probability, becomes predict, bracket, model, comma, new data equals data, dot frame, brackets, X equals new data, type equals response. You're going to add a logistic curve. So you're going to add a line, brackets, X new, comma, predprob, comma, color equals red, line width equals 2. So you run it, and this is what you have. This is your logistic regression. So your logistic regression basically has everything below everything below from -4 to +4 is the line that it's drawn. And so we're going to come over here and see if we can find what the predictor is. I can't see it, but it's generally going to be 0.5. So everything less than 0.5 is going to be 0, and everything above 0.5, above or equal to 0.5, is going to be 1. So that means you only have 2 outputs, either a 0 or a 5. And this is the diagram that is presented showing your logistic regression curve. And then so the probability of y equals 1. So if it's a probability of 0, it's definitely going to be a 0, and the probability of 1, it's definitely going to be a 1. So that was a simple logistic regression problem. Now what we're going to do is we're going to calculate the accuracy of the above problem. We're going to fit the logistic regression model becomes GLM, that's general linearized model. And your predicted probabilities for p hat becomes predict brackets model, comma, type equals response. We're going to convert to class predictions using a threshold of 0.5. So that means everything below 0.5 is going to be a 0, and everything equal to or above 0.5 is going to be a 1. So y pred becomes if else brackets p hat greater than or equal to 0.5, comma 1, comma 0. So that's just basically what I just stated, but it's stated in our code. We're going to calculate the classification accuracy. So mean brackets y pred, that's your prediction, equals my data $y, and that's your y values. And it has an accuracy of 90%, which is not too bad. So what we're going to do now is we're going to create a confusion matrix of the above model. So table brackets predicted equals y pred, and actual equals my data $y. So your predicted is going to be a 0 or a 1, and so that means on the zeros you have 106 zeros that and 10 of those and 10 ones. So that means 106 are true positives and 10 are false negatives. And then you have 1. So you have 10 zeros and 74 ones. So you have 74 true negatives and 10 false positives. So that's a confusion matrix that is created for the above model. Now we're going to demonstrate a 3-class, that's a multinomial logistic regression model. And that's done a little bit differently in R, but you can do it. And we're going to be using the one versus rest strategy. So we're going to simulate a 3-class data. First thing that you're going to do is you're going to set your seed so that every time you run the program, the variables are going to be initialized to the same value. So set.seed brackets 1, 2, 3. N is going to be your number of samples, and it's 300. X1 becomes R norm N, so that means a randomly sampled normal distribution of 300 samples. And I think that when you have a normal distribution and the mean and the standard deviation are not defined, the mean is going to be 0 and the standard deviation is going to be 1. And then again on X2, you have another normal distribution randomly sampled with 300 samples. And then we're going to have the true class based on linear boundaries. Eta 1 becomes 1 plus 2 times x1 minus x2, and eta 2 becomes negative 1 plus x1 plus 2 times x2. Prob 1 becomes exp eta 1, that's exponent. Prob 2 becomes exp at a 2, that's an exponent, and prob 3 equals or becomes 1. So total equals prob 1 plus prob 2 plus prob 3. So P1, that's your probability of 1, becomes prob 1 divided by total. P2 becomes prob 2 divided by total, and P3 becomes prob 3 divided by total. So Y becomes apply, bracket C bind, brackets P1, P2, and P3, brackets, comma 1, comma function P, and then it's sample brackets 1 to 3, comma 1, comma prob equals P. And then my data becomes, you're going to create a data frame from everything that you've just defined. So my data becomes data.frame, brackets, Y equals factor, brackets, Y, brackets, comma, X1, comma, X2. And then we're going to fit 3 versus rest model, logistic models. So model for class 1 versus others is M1 becomes GLM, brackets I, brackets Y equals 1, brackets tilde X1 plus X2, comma, data equals my data, comma, family equals binomial. Model for class 2 versus others is M2 becomes GLM, that's your general linearized model, brackets I, brackets Y equals 2, brackets tilde X1 plus X2, comma, data equals my data, comma, family equals model. And then model for class 3 versus other, M3 becomes GLM, brackets I, brackets Y equals 3, brackets tilde X1 plus X2, comma, data equals my data, comma, family equals binomial. And then we're going to predict the class membership. So P1 hat becomes predict, brackets M1 type equals response. P2 becomes predict, brackets M2, comma, type equals response. P3 hat becomes predict, brackets M3, comma, type equals response. We're going to normalize the sum to 1. So P, capital P, becomes a C bind, brackets P hat, P1 hat, P2 hat, P3 hat. And then capital P becomes P divided by row sums of B. So pred class becomes max.call, capital P, and then we're going to calculate the classification accuracy, mean, brackets, pred cells equals my data, $y, and so you have an accuracy of 73%, which isn't fantastic, but that's just one way that you can carry out multinomial logistic regression in R. Because if you're trying to do multinomial logistic regression in Python, Python has a library called sklearn that you can import, and in sklearn's library, they've got a function for logistic regression, and on logistic regression you can do it as a binomial, which means 2 outputs, or you can also do it as multinomial. But they don't have that in R, and since they don't have that in R, you have to perform multinomial logistic regression in a roundabout fashion using the one versus others method, which is the method that I showed you. So, if you want to do multinomial regression, it probably would be easier to do it in Python using sklearn. But if you don't have Python available, then this is a way you can do it using R. So now what we're going to do is a case study. So a company wants to predict whether a customer will purchase a product, which is 1, or not purchase a product, which is 0. So we're going to simulate our data. So we're going to and then we're going to set our seed. So whenever you set your seed, every time you run the program, the variables are going to be initialized to the same value. So you do that by typing set.seed brackets 1, 2, 3, and you can type any number that you want within the brackets. So n becomes 400. So this n is going to be the number of samples. So age becomes R norm, brackets n, comma, mean equals 40, comma, standard distribution equals 12. So that is a randomly sampled normal distribution of 400 samples with a mean of 40 and a standard deviation of 12. So your income is also going to be a randomly sampled normal distribution, and it's going to be 400. That's the number of samples. Mean is 55,000, and standard deviation is 15,000. And the duration becomes, again, a randomly sampled normal distribution of 400 samples with a mean of 5 and a standard deviation of 2. So we're going to have the true underlying log odds model. So ETA becomes -8 plus 0.04 times age plus 0.00006 times income plus 0.35 times duration. And capital P becomes -1 divided by brackets 1 plus exp, that's exponent negative eta. And then purchase becomes R binom. That's a randomly sampled binomial distribution with 400 samples, size of 1, and a probability of B. Okay, so you're going to have your my data is going to be converted into a data frame. So equals my data.frame, brackets purchase, age, income, duration. And then we're going to explore the data. So we're going to summarize my data. So this is a summary of the data. So you've got purchase, age, income, and duration. You have the minimum value, the first quartile, the median, the mean, the third quartile, and the max. So the median is like the center element in the vector. And the mean is the number of elements in the vector divided by the sum of all the elements of the vector. So the median for purchase is 0, and the mean is 0.245. But you've got your median age is 39.60, and the mean age is 40.20. So that means that the median age is going to be the center value within a vector, and the mean is going to be the number of elements in that vector divided by the sum of the vector. And then you've got your income and your duration. And then so when we run the program, Let's go back. So we've summarized the model. Well, we're going to fit the logistic regression model. So model becomes GLM, that's general linearized model, brackets purchase, tilde age plus income plus duration. So purchase is your Y variable, and age, income, and duration are your X variables. Data equals my data, and family equals binomial. So we're going to summarize the model. So in your outcome, you have 302 zeros and 98 ones. So that means 302 customers didn't purchase the product and 98 did. And then when we summarize the model, the GLM, in brackets, formula equals purchase, tilde age plus income plus duration, family equals binomial, date equals my data. And then you have coefficients. You've got your intercept, your age, income, and your duration. So you've got an estimate, standard error, a z-value means that this is based on a normal distribution or a z-distribution, and then you've got a p-value. You've got your significant codes, and then you've got a dispersion parameter for binomial family taken to be 1. You've got null deviance, and you've got residual deviance, and you've got your AIC, which AIC is a goodness of fit test that is used in statistics. So we're going to interpret the results. So the interpretation of the results is that older customers have a slightly higher odds of purchasing. Higher income customers are more likely to buy. Every extra minute on the website increases the odds of purchase sustainability, and the duration will almost always be highly significant because of a strong effect is simulated. So now we're going to take the odds ratio, converts log odds to multiplicative effects. So EXP brackets coef brackets model. And then we're going to predict the probabilities. So P hat becomes predict brackets model, comma, type equals response. We're going to convert the probabilities to class predictions. So pred class becomes if else brackets P hat is greater than or equal to 0.5. It's going to give you a 1. Otherwise, it's going to give you 0. We're going to calculate class accuracy. So mean brackets pred class equals my data $ purchase. We're going to plot the predicted probability curve. So we're going to create new data for plotting. So duration new becomes SEQ, that's the type of vector, brackets min duration, comma, max duration, comma, length out equals 200. And then we're going to plot the data. So plot data becomes data.frame, brackets age equals mean age, comma, income equals mean income, comma, duration equals duration new. And then the prob curve becomes predict brackets model, comma, new data equals plot data, comma, type equals response. So plot the data. So plot brackets duration, comma, jitter, brackets purchase, comma, amount equals 0.05. PCH is the size of the dot, it's 19. Color is RGB, and that's a vector that's used for colors. Brackets 0, 0, 1, 0.3. XLab is the label on the x-axis, which is website visit duration in minutes. YLab is the label on the y-axis, which is purchase bracket 0/1. And then main is the title. It's logistic regression, purchase probability versus duration. And then we're going to put some lines in there. So line, brackets, duration, new, comma, prob curve, comma, color equals red, comma, line width equals 2. And then, so we go through what we've done in the program. So we run the program. So you have the number of Fisher scoring deviations is 5. That's another statistical variable. And then we've got our chart being logistic regression, purchase probability versus duration. So basically what they're saying is that the longer that they visit this website, the more likely they're going to be to purchase a product. And so on the x-axis, you've got website visit duration in minutes. And then on the y-axis, you've got purchase 0,1. So basically what they're saying is the longer that you stay on the website, the more likely you're going to be to actually purchase the product. And then so you've got your 0, which means that they didn't purchase the product, and the 1, which means they did purchase the product. So that concludes this video. I hope that you got something out of it. The next video is going to be another statistical subject in R, and I hope that you decide to watch it.